Hello everyone! Once again, welcome to Small Terrible Channel. This is Mr. Aseno, your science teacher for today. Today we're going to discuss session 4 entitled Circular Motion. This is still graded science, unit 1, force, motion, and energy. Ready? Okay, there we go. So still we are in quarter 1, week 1, learning competency. Relate the laws of motion to bodies in uniform circular motion. Second, infer that circular motion requires the application of constant force directed toward the center of the circle. The session objectives describe the motion of an object moving in a circular path. Using diagrams, determine the direction of the force, acceleration, and velocity of an object moving around a circular path. Explain the relationship between the centripetal force and the speed or velocity of an object moving in uniformly circular motion or UCM. Lastly, explain the relationship between the speed or velocity of an object moving in UCM and the radius of the circular path. So let's recall. You're going to determine which among Newton's three laws would apply to the following situation. Could be letter A, Newton's first law, B, Newton's second law, C, Newton's third law. Since we're done discussing in our previous three sessions about the Newton's three laws of motion, let's try to check how much you understand the concepts. Okay, ready? Are you ready? Here we go. Number 1, when you dive off of a diving board, you push down on the springboard. The board springs back and forces you into the air. What law is applicable in this situation? Okay, it should be letter C, Newton's third law or the law of interaction. Second, you're diving. Number 2, you're driving your car at a very high speed and hit something like a brick wall or a tree. The car will come to an instant stop, but you will keep moving forward. So what law is applicable or depicted in this situation? Should be, of course, letter A, Newton's first law of motion. Okay, Newton's first law. Third, or number 3, it is easier to push an empty shopping cart than a full one because the full shopping cart has more inertia, means mass, than the empty one. Should be? Okay, there we go. That should be number 2, Newton's second law or the law of acceleration. When an object is acted upon by a net force, it accelerates. It changes its state of motion. So when a force acts on an object, the following may happen. First, it moves from being at rest. Second, it stops from being in motion. Third, it changes its speed. Sorry. Speed up or slow down. Maintains constant speed but changes its direction. So let's try to watch this video. This is related to our topic for today, circular motion. Right? Are you ready? Here we go. Okay. So this video represent a wall of death. Okay. Here we go. Okay. Can you do that? You see the girl driving in the wall of death. It's very amazing. This is another daredevil. Let's see what he can do. Ooh, amazing. Amazing. Awesome. That's simply amazing. Wow. Wow. This guy is amazing. This guy is amazing. This guy is amazing. This guy is cool. Look! Wow! This guy is a Superman. Wow! Oh, cool. Alright, there we go. So, how are the daredevils able to perform the wall of death stunt? Isn't it amazing? So, let's try a marble lift challenge. This is a, you can do this at home or you can do this by group. So, the task of the group is to lift up the marble with an inverted wine glass or a wide mouth jar. So, this is how you're going to do this. Okay, this is the picture. So you're going to have a marble, and then you are going to use a wine glass. Then you should be able to uh, put the marble inside the glass without holding it. Okay, but just using the glass. We call that marble lift. So this is a good demonstration for circular motion. Can you do it? Okay, you try. Now, these are the following guide questions after the activity. What enabled you to transfer the marbles without touching the marbles? What kind of motion is required to transfer the marbles? Is it necessary to sustain the motion of the marbles inside the jar to keep it from falling? What would happen to the marble if this motion suddenly stopped? As the marble moves around the jar, how many forces are acting on it? Draw the forces acting on the marble while moving inside the jar. Okay, you can use one half manila paper to draw your illustration. So the science behind the marble lifting. So the friction between the jar and the marble and the force of the earth on the marble, as gravitational force, would balance out each other. Otherwise, the marble will stop. Okay, nothing will balance the support force of the glass and the marble. So it would be the net force on the marble. Since there is a net force on the marble, what happened to it? Okay, these are the demonstration. You have three forces, vector forces. So this the black represent the marble. Okay, you have the blue arrow represent the frictional friction between the jar and the marble. So if you observe, this should be a kinetic friction. It, it is going up because others. This is actually it should be going up because the friction should prevent the ball from falling. And force of the earth on the marble, as well as the gravitational force. And you have support force of the glass on the marble. So you have there are three forces there. So the object is accelerating because it's changing its direction of motion every point in the circular path while maintaining its constant speed, noting that the object travels the same distance because the radius of the circular path is not changing. So uniform circular motion, a type of motion of an object in a circular path with a constant speed but changing direction due to a net force. That's the definition of uniform circular motion. So you have there the illustration. Centripetal force, centripetal acceleration. So you have there different forces. You have V stands for velocity, which is represented by the black arrow. You have the FC, the centripetal force. If you observe what is the direction of the centripetal force or the FC, it is towards the center. Because the FC or centripetal force is towards the center, the centripetal it has a centripetal acceleration. The acceleration is centripetal, going to the center. So circular motion. In circular motion, the direction of the velocity changes every point along the circular path. This change in direction is an indication that the object is accelerating and the direction of the acceleration is towards the center of the circular path. Thus, it is called a centripetal acceleration. So, there is acceleration. Why? Because the change in direction is an indication that the object is accelerating, and the direction of the acceleration is towards the center of the circular path. That is path. That thus it is called a centripetal acceleration. So basically, it is called it is accelerating not because the motion is changing. The velocity, I guess, is still the same, but what changes is the direction. Okay. Following Newton's second law, centripetal acceleration is caused by a net force. There should be a net force, okay, because there's an acceleration. Remember, force is equal to mass times acceleration. There should be a relationship between force and acceleration. Without force, there is no acceleration there actually. Following the Newton's second law, centripetal acceleration is caused by the net force, that is the centripetal force. So how do you call the force when it comes to circular motion? The centripetal force. That's what happened during the wall of death. Okay, how are the daredevils able to perform the wall of death stunt? So this is the explanation. Okay, draw the possible forces that will act on the motorcycle and the rider while moving along the wall of death. So you can create your free body diagram to explain why. So you have there three forces: friction, normal force, and weight. So the friction is going up. Remember, the frictional force should prevent the motorcycle from going down. That is why the direction is going up. On the other hand, it is the opposite for frictional force is weight of the motor cycle on the man. Then you have the normal force exerted by the wall on the motorcycle, the normal force. Okay. Let's view the wall of death from the top. So when you look at it at the top, this is what happened. So you have gravitational force, they have the red, and then the blue frictional force, and then the support force. If you observe, the support force is always going to the center. So the support force is centripetal by nature. We call that centripetal force. Think, what will happen to the motion of an object moving in circular motion when the centripetal force suddenly disappears? What will happen? So you think about it. Okay. So this is another demonstration for the centripetal force. Okay. So this will answer the question, what will happen to the motion of an object moving in circular motion when the centripetal force suddenly disappears? Look at the demonstration. So this is a great demonstration of a circular motion. If something is going on a circle and you remove the centripetal force, if you observe the light that is going out, it is when you remove the centripetal force, that's what happened. Okay. So actually, this is a simple way to demonstrate the circular motion. Okay. Okay, there we go. Okay, let's place an object here, the card. Okay, what happened when we lift the hook? Okay, the bullseye is going around, but when we lift the hook, when it loses the centripetal force, it will hit the card. So it will go off with a tangent. It will go straight. It will follow the Newton's first law of motion, actually. Okay. So the ball goes from moving in a circle to moving to a straight line after you remove the hook, because it's loses the centripetal force. Okay, what happened when it is on the hook? Okay, if you observe, the hook exert a perpendicular force, and the force is going always to the center of the circle. That is why it's called centripetal force. When you take away the centripetal force, what happened? It obeys now the Newton's first law of motion. It will move to a straight line and then hit the card. So this is true of all objects that is moving in a constant velocity in a circle. When you remove the centripetal force, it will move to a straight line when you remove the centripetal force. Okay, so actually, a centripetal force simply only signifies a direction of the force that is going to the center. Still, there is a contact force that is between the hook and the ball. Okay, so when we talk about centripetal force, it simply means the direction of the force. Okay. Okay, so at point A, the velocity vector of a body moving in circular motion is directed tangent to the circular path, hence the term tangential velocity. If you observe, if the object is moving in a circular path, this is the radius distance from the center. So if you observe, it's going there, but if you remove the centripetal force, it will move to a straight line. Okay. Because of the centripetal force, even if the speed of the moving object remains constant, the direction of the motion changes, and so the velocity changes in every point along the circumference of the path. Now, in the event that the centripetal force suddenly disappears, what will happen if you remove the centripetal force? There will be no net force that would make the objects accelerate, and so due to the object's inertia, it will continue to move in a straight path tangent to the original circular path. So when you remove the centripetal force, the object will move in a straight path tangent to the original circular path. So which path? Let's try to answer this. Which path in the figure at right would the ball most closely follow after it exits the channel at R and moves across the frictionless tabletop? What do you think? Remember, when you remove the centripetal force, the object will move in a straight line tangential to the original centripetal force. So what will happen? Which among these? A, B, C, D, E. Which one? It should be letter, of course, obviously letter B. It should move in a straight path, tangential to the circular path, original circular path. A steel ball is attached to a string and is swung in a circular path in a horizontal plane as illustrated in the accompanying figure on the left. At the point P indicated in the figure, the string suddenly breaks, near the ball. If these events are observed from directly above, as in the figure, which path would the ball most closely follow after the string breaks? Remember, the string breaks, so the centripetal force was removed. What do you think? Which path the ball will follow? Okay, should be what? Answer should be letter B. It should be still a straight line, but the possible answer are B or C, B or E. But it should be straight line and tangential to the original circular path. So the answer is letter B. You can do this experiment. Okay? You can attach something and then try to move it in circular motion, turn it around, like spin it, and then release the string. You will observe this phenomena. So are you familiar with the hammer throw? It's an Olympic game. So this Olympics have started. Might participate in the hammer throw. So Thor wants to participate in the hammer throw. Remember, he is the strongest Avenger. So what if Thor really do hammer throw? Okay. What if let's try hammer throw? Okay. You have there the velocity, the red arrow, the green acceleration, and you have centripetal force. Remember, centripetal force is going to the center because it signifies direction. Now, the velocity of an object moving in uniformly circular motion, or UCM, is tangent to the circular path. The centripetal force and centripetal acceleration are both directed radially inward towards the center of the circular path. Thor is participating in an Olympic game of hammer throw, literally, as in literally. He aims to throw his hammer with the fastest speed as possible. Now, there's another guy. You know this guy is Iron Man. Okay. Tony Stark, Iron Man, wishes to challenge Thor and test his physics competence, and he suggested that Thor should attach a chain on a hammer so as to make it swirl with larger circumference and thereby producing faster speed in throwing the hammer. Is the suggestion helpful to Thor? Is the suggestion of Iron Man helpful to Thor? Remember, the aim of Thor is to he aims to throw his hammer with the fastest speed as possible. So, is the suggestion of Iron Man helpful to Thor? Let's find out. We find out. Anyway, this is an activity. You can do this. Anyway, this is quite long, but it's very exciting activity. You can do this inside at home. So Tony Stark wishes to challenge. So what would be what would be their answer? Is it helpful? No, the answer is the Tony Stark suggestion is wrong. If a chain is attached to Thor's hammer, it would make the radius of the circular path of the world hammer larger. Thus, the speed of the hammer's revolution would be slower. So the suggestion of Iron Man is not helping Thor. The radius of the circular path of an object moving in a uniform circular motion is inversely proportional to the speed of the moving object. And remember, radius of the circular path of an object is inversely proportional to the speed of the moving object. The higher the radius, the slower should be the speed of the moving object. Okay. All right. So summing it up, the time to complete its 20 revolution becomes larger and longer as the length of the string attached to the stopper is increased. This indicates that the speed of the of the object moving in uniform circular object decreases or becomes slower. The speed magnitude of the velocity of the moving object is inversely proportional to the radius of the circular path. As the radius of the circular path increases, the time to complete a revolution becomes larger, thus making the speed slower. Okay. Let's check your understanding. Okay. So number one, in a circular motion, what happens to the distance traveled by the object when the radius of the path is increased? A, the distance traveled is increased. B, the distance traveled is decreased. C, the distance traveled remains the same. That should be the answer? Should be A, the distance traveled is increased. Next, in circular motion, what happens to the time to complete the motion when the radius of the circular path is increased? Okay, remember the relationship. A, the time to complete the motion is increased. B, the time to complete the motion is decreased. The time to complete C, the time to complete the motion remains the same. In circular motion, what happens to the time to complete the motion when the radius of the circular path is increased? So of course the time will also increase. The time to complete the motion is increased. Okay. Next, in circular motion, what happens to the speed or magnitude of velocity when the radius of the circular path is increased? Okay, the relationship between magnitude or speed and the radius of the circular path. So what happened? So remember that A, the speed or magnitude of the velocity increases. B, the speed or magnitude of the velocity decreases. C, the speed or magnitude of the velocity remains the same. D, the speed or magnitude of the velocity becomes zero. What do you think? The relationship, remember the relationship between radius and speed. So of course, letter B, the speed or magnitude of velocity decreases. Thank you very much. Very much, rather. Bye-bye for now.